Hello, this is Brian Baker, and today I'd like to speak about the efficient FASTQ Phred quality scoring using BioPython. This presentation aims to demonstrate how to obtain Phred quality scores as quickly as possible using the available methods within the Python programming language. In addition, I'll examine how to identify patterns within the quality scores, such as low-quality distributions, to help ensure the accuracy of the nucleotide data. Phred quality scores measure the probability of correctly identifying a nucleotide within a given DNA sequence. The default standard format for storing short-read sequencing data is FASTQ. This was initially developed by Wellcome Trust Sanger Institute, and this format combines the FASTA format with quality scores. This presentation will evaluate two methods to obtain a Phred score and focus on the more efficient method utilizing the Python programming language. The manual method requires an ASCII lookup table by which one can manually compute each nucleotide's Phred quality score with the aid of mathematical formulas. The quality for each base indicates the probability of a base calling error. The higher the quality score, the higher the accuracy. To manually compute a Phred quality score, each base is first converted to a decimal value from an ASCII table. For example, if the letter I is located below a nucleotide character within a sequence, the corresponding decimal value for I within the ASCII table is 49. The Phred quality score is offset by 33 characters, as only the 33 through 126 are usable characters, so the Phred quality score Q will be 49 minus 33, which is 16. So for a quality score of 16, after using the formulas for P, one can obtain the value of P at 0.0251 or 2.51%. A random severe acute respiratory syndrome coronavirus 2 FASTQ read file was chosen from the European Nucleotide Archive to demonstrate how to quickly compute its Phred quality score. By issuing the following wget command, a specific FASTQ file was retrieved after reviewing several candidates on the ENA website. The seqio module was imported from the BioPython library to parse the file's FASTQ contents. Once parsed, the record containing the first read can be parsed into its constituent components, into a dictionary object, via available seqio methods such as ID, description, sequence, and annotations. The annotations are the Phred quality scores that are computed by the Python SQI library. After the Python code prints the parsed components, the code proceeds to count the number of records, iterates through each one, reads each letter within the sequence, and creates an array for each unique nucleotide. And then it sums the totals for each one. Finally, the totals are computed into percentage fractions of the total nucleotides. The unknown base N can now be investigated to determine where within the sequence the locations it occurs most often. Again, the FASTQ file is unzipped and processed by iterating over the dictionary of records one nucleotide at a time and then checked for the value of N. If found, the count of N is incremented by 1. The number of N versus position is then plotted on the screen utilizing the functions found within the matplotlib library. The plot shows that the N values begin mostly after position 65. The N values appear to be position dependent, but slightly erratic in this particular FASTQ file. The following Python code parses the FASTQ file to investigate the Phred quality distribution even further. Then it iterates over the dictionary of unique Phred quality scores to increment by 1 for each new Phred score. The totals are calculated for each unique score and converted to percentage fractions of the total amount of nucleotides found within the sequences. The output reveals that the quality score of 37 is the most frequent score at 87%, which is the desired outcome, as the higher values indicate higher probabilities that the base call is accurate. However, other quality scores remain, such as 25 and 11, and notably the 0 score, which is of little to no value in terms of an accurate read. So in conclusion, the previous analysis utilized Python libraries such as BioPython, and it demonstrates its effectiveness in providing insight into the distribution of the nucleotides and the quality of their associated read scores. These observations of the sequence data further enhance future explorations into the dataset and reveal patterns that indicate where low-quality scores cluster within the specific locations of the sequences. The low Phred scores may either be safely ignored, if not relevant to the specific bioinformatics investigation, or it may serve as an incentive to pursue additional reads from other formal studies to ensure the accuracy of the data for a future research project. Thank you.